Okay, let's go. Hello, everyone. It's been a while. This is the first stream of the year. I was intending to take a longer break over the holidays, and then I procrastinated doing my new OBS setup, and then it had been a few months since I had streamed, so I had to figure out where to start again, and then it was March. So yeah, welcome back to the stream. I'm gonna basically just jump back where we left off, but before that, I would like to, I think, start with a quick recap of where the project is basically 1 year in. So far, in our quest to compile Rust like code into an image, what do we have? Well, our language for now looks something like this. We have a test file here. We're able to declare functions that can have generic type arguments. We have structs that also can be can have arguments. We have constants. We have a bunch of things like this that look like Rust code. There's one exception we have made in the syntax of the language because of the limitation in the parser, which is that the syntax for the creation of a value of a struct type uses a at here rather than just being this like it would be in actual Rust. Now, from this, we've decomposed the work of compiling into an image in several steps. The first is the parser that gives us, if I go back here, gives us our basic AST. That's the parsed version again. So a module is a bunch of imports and a bunch of definitions, and a lot of things of the AST are here in common because we reuse the same structure for different phases of the AST. Our AST starts parsed, then becomes resolved, then becomes validated. We use the same types, but with a different type parameter, more or less. This is an approach that's called trees that grow in the original research paper that introduced it, to represent basically the evolution of our AST as we transform it. As it is parsed, if we go back to parsed, a path within the code, such as a variable name or a specific name within the module, is just a list of text. We have not resolved anything. Every expression is decorated with location information, which is useful for error messages. When we make error messages, we haven't done those yet, and so on. The first thing we do with the AST is we do a resolution phase. That's a big change we did in the summer where we broke down what was once one big analysis phase into two parts. The first part is the analysis phase that basically to every path, every name we encounter in the code checks where that name comes from and assign a role to it. So in the resolved version of the AST, we end up with a very similar thing, but now every path has a role that describes, okay, we found that this name at this location, for instance, if I bring back our test file here, when we have done this resolution, we have found that this path, test return struct, is in fact a function, and it points to this one that has been defined in the same file. So for each path, we have transformed into, hey, this thing maps to a built-in type, or to a built-in function, or a struct, or an enum, or something like this. We haven't checked that it is valid where it is. We've just done that work of resolving where the name comes from. Hello, welcome back. Sorry for the long absence. So that was the resolving phase, which gives us the resolved version of our AST. After that, we have the analysis phase that we have renamed, I think. How did we name it again? So if we look at the analysis, I think we broke it down into resolving and validation. So the validation phase looks now at this code and this AST in which we know what everything points to, like this is a type alias, it's a function, it's a constant, and we can now check that this thing is at the correct place. This is the core of the analysis phase. It is the part we've spent the most time on. This will be where we do things such as, if I go have a look at it, during the analysis, the validation, let's look at expression, for instance. This will be where we check that in a const expression, for instance, that if we find a function calling expression, in a function call expression, we are gonna throw an error to the user because function calls in constant are not allowed, that kind of stuff. This is also where we do type validation. At the end of this phase, we are still using a lot of the types that are part of our shared AST, but this time around it has changed a tiny bit. The validated thing now has void for the path body type. There is no longer any resolved path in the output. We have now mapped to other things. Expressions use a different type. They're no longer annotated with locations. We've changed the shape of the AST to better suit our needs. The phase after this is the lowering. We lower this AST that we have validated, that we now is correct, that we have type checked and everything. We try to generate a intermediary representation that represents what the code is like without being down to the level of like assembly, basically. This IR looks like this. A function is a series of blocks, and you can think of a block as like from a go-to label to the next jump, more or less. So we decompose a function into a series of sections, and each has a few basic instructions and which registers were given as an argument. We are using an approach where our IR is a static single assignment, and instead of using phi functions, which is what a lot of IRs use, we use block arguments, as in each block has a list of registers that it must take as an argument from a previous jump instruction. Now, the next phase after this, after generating the IR, will be code generation. But code generation is currently, well, undefined. That's the section. That's the part of the code we haven't done yet. Well, there's a lot we haven't done yet. A lot in the validation is still left with to-dos and unimplemented. There's a lot of work that's not done yet. But the phase for which we don't have anything yet is this generation phase. The output of which would be raw like assembly if this were a real compiler. This being our toy compiler, the output of this will be a kind of bytecode where those are basically the basic instructions of our target language, of our target architecture, which is the Piètre programming language. So this will be the output of the phase that we haven't started working on. We will get a bunch of just modifying the stack to do adds and pushes and stuff. After this, we'll do a linking phase where we resolve all of the addresses when we push an address on the stack. And at the end, we will do just generating an image. And those phases are already done, which is how we have generated the very first program a long while ago, which was this one, which prints 2 characters and outputs and does nothing else. But this was generated with the full backend of our compiler. So that's where we are roughly in terms of what we have done. In the next steps, I want to restart this stream this year by working on code generation, because we are so close to being able to take a test file and actually generate an image. We just need this to be like have some code there. When we have this, I think the next steps will be trying to do some visualization. I want to have a tool that exports the IR into something that can be visualized easily. I do have a small tool. Where is it? I have a thing like this that exports already, that allows for debugging, pretty printing of the past AST, the validated AST, and so on, with syntax highlighting and everything. But I think we can do better than this. And I would like to do something that visualizes the IR as a dot file. And possibly, I'm tempted to try to do a tool that exports our IR into the LLVM IR so that we can try to compile our Rust-like programs into actual programs. So that's the plan in the short term. For this evening, I think we're gonna try to write this function. And I think I'm not gonna keep any of this. We'll see. So the trick with this is we are gonna need to do basically a thing that's called register allocation in a real compiler. With the difference that since we are targeting a language that is stack only, we don't have registers. But it means we're going to have to think about the memory layout. And to do that, the usual algorithms for this, the most basic algorithms for this, like look at lifetime of variables. For instance, if I have, let's say, a piece of code that looks like this. I do a let a equals 3, and then I say let b equals a plus 5, and then I do let c equals a minus 1, and then down the line I have some if c is less than 0, then something happens, and here at the end I have a print b or whatever. Random code in a language that doesn't exist, but you get the gist of this. Now, this a classic way to do this kind of like, okay, in which register does which variable goes, is to look at the lifetime of this. A will live from here to here, basically. So that's the A lifetime. The B lifetime will be this. The C lifetime will be this. So now we can see when a variable stops, when a variable starts. If I had here, let's say, a let d equals 4 or whatever, I could conceptually put it inside the same register that you used to have A, because I know by that point that the A register is no longer used because this is the last place that A is used. So that's one of the ways to do this. In our case, since again we have only the stack, but we also have a lot of restrictions around the stack, because the only way we have to manipulate the stack at the Piètre level is with a roll instruction that requires pushing on the stack the correct values for the roll. I think the way I'm going to do this is instead, I'm going to try to do a thing where I start by what the end of a block must be like. What the shape of the stack must be like by then go back to generate basically so that I can associate to every instruction into my IR. This is what the shape of the stack after this must be like. That way I can then start from like the start of the block. What does roll do? Roll will roll the stack by the given arguments. I'm not completely sure I remember the order of the arguments, but if you imagine that the stack, I'm going to use characters for this. Let's imagine that the stack contains C and then B and then A, and the top of the stack is here, for instance. If I push, I don't remember the order of the arguments, but let's say 2 and 3, and now the top of my stack is here, and then I do a roll instruction, it will pop those two values to use as the arguments to the roll, and we'll roll the stack for a depth of 3, that argument, by 2 steps. And what that means is bring the thing that is at the depth 3 back up 2. So we will end up with C going back once, twice. So it will be there, which means A will be behind. So we'll end up with B, C. B, A, C. That is what a roll does. This is basically the only operation we have in the bytecode for actual stack manipulation, beyond pushing a value, popping a value. All of the other basic things like consume, I'll have to check. I don't remember if the output things consume a value of the stack, because here there would be some optimizations. Like if they do, there will be some optimizations such as, oh, this is the last time this value is used, we don't need to duplicate it. However, we'll have to make sure otherwise that if it's still used afterwards, then we duplicate it first. There is a duplicate instruction. Okay. Yeah, there is a duplicate, thankfully. Otherwise, things would get a bit messy otherwise. So that is what we have to do. I'm gonna just clean this for now. So yeah, I think the way I'm gonna do this is, again, associate going backwards through a block. Oh, and I should probably show what the block looks like. I'm gonna go backwards through a block and associate to each instruction, okay, this is what the stack should look like after this. That way we can then see what we can iterate through the list of instructions, see what the stack looks like after the previous instruction, see what it should look like after the current instruction, and generate the steps in between. One thing I should show, if I go back to the IR, so a function is a series of blocks, which again are from a label to which we can jump all the way to a terminator, which is a jump to something else. A terminator being a unconditional jump to another block, branching between two other blocks, returning out of the function altogether, or panic. And the instructions are those extremely basic things that are somewhere in between what our language supports. It has a notion of fields within a struct, for instance, which is something that we will have to translate into actual basic Piètre instructions, but it also has some basic add, subtract, multiply, and so on that will map one-to-one with Piètre instructions. Give me 1 second. Okay, so how do we do this? One thing I'm not sure about, I think as part of the code generation will be the stack manipulation for the return address. So the way, if I go back, oh, I closed it. That's fine. The way the return of functions work is this structure I have around, which might change, is that whatever value is on the top of the stack when we exit a function is the address to which we are jumping. What do you mean over? No, I don't have over. So if I want to do a duplicate like the one you suggest, I have to do a roll to put A on top, duplicate, and then do a roll again to put it back below. So what that means is when I enter a function, the thing that's below the arguments on the stack will be the return address. But when I leave here, the return address must be on top of the output values of a function. And hello, everyone. And that means I will probably need to do code generation to be aware of the return address. So I think this piece of the code will have to be aware of, in fact, there's another register that needs to be through all of this, which is the return address. That, or maybe I don't, because it makes everything complicated, because I would need to change my IR generation to have it pass as an argument from label to label, which I don't want to do. I could just assume that it's always right below the argument, which means that whenever I generate the code for a return, I just need to insert a roll of 1 at the depth of the number of bytes, a number of cells of the return values. Yeah, that's probably fine. Okay, let me also do a quick thing. I think if I do, I don't need to do that anymore because I no longer have the webcam obscuring the first few line. If I do this, do I still have something that shows me the IR? I do. Okay, perfect. So I can show you what the IR looks like before. There will not be any GenAI in this stream. I am profoundly opposed to GenAI. I will not use GenAI. There is no GenAI here. And if you hate GenAI, you're welcome here. But yeah, this is what our IR looks like. Here's the... Oh, thank you for the follow. If I go back to this test file, I have a function here. Let's look at one of them. Let's look at one that's interesting, one that has more than one label, perhaps. All of those are very basic. All of them have only one label. That's not very interesting. Do I have a more interesting test file somewhere in this great naming scheme of mine? Do I have a test 4? I do have a test 4. Incredible. Let's go. Well, to be clear, it's generative AI I don't like. LSP is perfectly fine. I don't use the one for Haskell mostly out of habit, because when I used it, I tried to use it 6 years ago. It was a bit slow. I have absolutely nothing against it. I'm not a technophobe, which I hope this stream demonstrates. I just don't like the current trend of GenAI for a lot of reasons. Okay, so this function is a lot more interesting. That is in test 4. And it is bar. Great name. Incredible. So, okay, we have this function here, bar, that does let x equal 0, while x is greater than 0, and if, and so on. This gets translated into this. The first label is the starting label of the function. We assign a 0 to a first register, i0. We jump unconditionally to label 1, which will be the loop condition, I believe, which does a compare operation, which branches between label 2 and label 3. Label 2 will be, I think, the loop, and label 3 will be after the loop. Yes, because label 3 is after the loop, it's the return. So label 2 is the body of the loop, where we do the assignment, modulo, assignment, compare, and so on, and then we branch based on the value of a register. And that branch would be the if I'm not mistaken, this one, which branches either to label 5 or label 4. 5 is a return, so 5 is the inner if here, where we have a few things to do. And 4, including a function call, which is the invoke instruction. And label 4 is the jump back to the loop condition block, which was label 1. So to translate this IR into actual code, we're going to go through label, like block per block. And again, we can know what the shape of the stack needs to be at the end of a block by looking at its one terminator thing. When we jump to label 1 with those arguments, we know that the only thing that is required moving forward is this particular value. So whatever is in this value is the i13 register is what we need moving forward. Whatever it ends up being on the stack, that's the only value we need. The problem with AI, I don't want to get too sidetracked with AI stuff, but as people smarter than me have pointed out, AI is a marketing term. AI is a field of research. The things we have today under the umbrella GenAI are not artificial intelligence as much as as some of the proponents like to claim that they are. So it is the bit of a problem of like when you paint all of AI, the research field, with one big brush. Yeah, machine learning is a good thing. Automatic classification of things is good. There's a lot of progress that we don't want to throw away. Generative AI and the current push for it is what I am opposed to. But AI is, again, kind of a marketing term. Okay, so again, the goal is we go through a block by block. We know what is required at the end of a block by looking at the registers that are um, at the. Well, it depends. I guess it depends on like, do you perceive LSPs to be? I don't know if LSPs do any kind of machine learning or anything. I don't know if they would qualify as AI. But yeah, anyway, we look at the output of this, we know what the stack looks like, and we can go back in time and know what registers are used beyond that fact. So let's get started with the code for this. So I think this will be correct. I'm not going to change this in the sense that a function is a bunch of blocks which are basically independent from one another in terms of code generation. So it just means for each of them, I put an entrance and I just generate the code for a block. A block is this thing. I'm going to keep the IR in scope here so that I know what a block is. There we go. And here I was starting by generating terminator. I think this whole thing goes away. Okay. So what we're going to want to do is start by, I put this as a comment for now. We are going to want to start by associating with each instruction of a block, which is the instruction there. We will want to get associated to it the list of registers that are required past this point, I think. So, and do we want to, do we care about the order of them at all or not? Okay, to explain what I am, to explain what I'm wondering about, basically what I'm saying is my code will start by looking at a block. Let's say, let's look at an interesting one. This one, for instance, we'll look at the end and say, okay, at this point, we will need I13. So I know that when I do the code generation for this instruction, the only register I care about past this point is I13. But I know that here I will need to care about I11 and I12, so I can move back to this instruction and say, past this point, we need I11, I12, I13, and so on. The question I'm wondering is, do I care about the order? So do I sort them as a list or as something that maintains an order, which might make searching for it a bit slower? Or do I not care about the order? I just care about, oh, those things are going to be needing moving forward, and I can make them a set, which makes search a bit faster. I think this is the question of order is purely a matter of optimization. So I think for this stage, we don't care. So I think I'm going to make that a set for now. So first, we will start by something that, given a terminator in the IR, gives me a hash set of register. Is register hashable, actually? It is not. Probably because it carries a type That being said, every register is uniquely identified by an index, so it should be easy. Yeah, this show instance is not great. I want to fix that at some point, but I can, for now, add a cord and the instance hashable for the register that makes it hashable for a hashing container such as a hash map or a hash set will just be hash with salt s of a register, and that is going to be hashing with salt s the register index, because a register will be uniquely identified by its index within a given function, not even within the block. So here, this is going to give me a set of registers that are required for the end of a function, and that is going to be a very basic case of our terminators. Where are they? They're here. Let's start with the most easy case. In the case of a panic, there is no register that needs to be saved because the code will be panicking anyway. Therefore, this is going to be just an empty hash set. Let me add import data hash set qualified as S to the things we're going to need as part of this file. Now, I need to look at what a target is. A target is a label and a list of register. Okay, so in a case where we jump to a given target, I'm going to actually name variables explicitly. Oh, I'm a bit late on the chat. Sorry about that. There is no thing called inheritance technically in Haskell. What thing exactly on screen made you think there was inheritance? I'm curious. Would that be, is that the deriving keyword? If yes, it is something else, and I'm happy to explain. So deriving is just a thing. Haskell has a thing called type classes, which are extremely similar to what other languages call traits, which are somewhat similar to what other languages like call interfaces, for instance. Show is basically the equivalent of what Rust calls debug. It is kind of a two-string interface in a sense. The big thing of Haskell, like Rust, like languages with traits, is that the definition of a trait instance or type class instance in Haskell parlance is not tied to the definition of the type. So here I'm deriving show, but let's remove this. I could instead say, well, actually, my type implements show by saying instance show terminator, where, and it turns out that the thing that show requires, the only thing in the show interface is the function show, and then I would implement the show function here. But for a bunch of them, the compiler is able to generate a definition for me, which for a lot of them is absolutely good enough. And the deriving keyword is just, okay, just generate a good enough instance of show for me. So this creates a show instance for Terminator, so I don't have to write it myself. However, as I've done here I have a custom instance of show, which is extremely temporary as indicated by this, which was used for debugging purposes, that doesn't use the default compiler one, but instead uses a custom one that I've made for debugging purposes. And a bunch of instances, in fact, cannot be derived automatically with this mechanism. So here, for instance, to make a register hashable, I could not just do a hashable here. So I did declare the instance myself, saying that, okay, how do we make a register hashable? We implement the hash with salt function, which is the only thing required to make it hashable. And here's the implementation. And we just hash the index. So here I have a jump terminator at the end of a block, and it's jumping to a given target, which is this thing. So the set of registers that are required to do this jump is this list here. So the set of registers that we're going to require will be a set from list of the target arguments of my target. Now, if we have a branch, then first we have a register here. I'm gonna again err on the side of very explicit name. We have a branch instruction that branches between two branches based on the value of a register here. This will be, therefore, the union of the sets obtained from each of those. I am tempted to make a small helper function from target is a function I don't need to type, which is basically given a target gives me a set. So this is going to be basically the composition of getting the arguments and creating a set from that. So this becomes now from target. This here, in the case of a branch, becomes a union of three different sets, what I'm going to rewrite this as, from target branch 1, union from target branch 2, union singleton of the register. All right, I'm going to animate condition so it's more clear. Okay. When we have a return, this is interesting. We may or may not have a register here, so it will depend on whether this maybe value here contains a value or not. So this is gonna be a maybe. In the case where we don't have a register inside, so there's no return value, then it's an empty set. Convenient. And in the case where we do, the function that we are applying is just singleton, and we apply this maybe function on the return value. And finally, panic is, again, this very basic thing. Okay, so that function that we have here now gives us, for the terminator of a block, the registers that we need at the end of a function. Okay, so now, if what we want to generate is, again, if I go back to a block, so the parents that is used for making the graph when we do control flow analysis, this is not going to be really required at this point. The arguments are the registers we're going to start with, but that's not something we care right now. Right now, what we want to do is transform this list of instruction into a list of instruction and set of output registers. So we can do that by doing basically a fold over the thing. However, we want to do a fold that transforms the list instead of actually. So what we want to do, let's see if Google has something for us. I want a function that, given some value x and an accumulator a, gives me some value b, and I want to apply this on a basic accumulator a and on the list of x, and I want the result of this to be a list of the x value unchanged, but accompanied with the a. Nothing found, no result found. Maybe I've been too... Oh, because I've been... It should be a b here. Not even that. Okay. So let's have a look at data list and see if there's something that in there Oops. That's because I am on the wrong... Okay. I thought scan and some of those functions... Well, almost, except this doesn't maintain it. I guess scan returns the value of the accumulator. And I could... Hello. Yeah, I'm sorry. I took a long break over the holidays that ended up lasting several months. The thing is, this is kind of a... do I want to just write this function? Maybe this is a bit more what I want. Map and fold. It applies a function to each element of the structure, passing an accumulator parameter from right to left. That is what I want. Perfect. So given the A, so S is our accumulator, the A are the values in the traversable structure, our list in this case. Given a value of the accumulator and an A, which is the value in our list, we return new accumulator and a B, and this B. Okay, perfect. So map accumulator R is what I want. So, to start with, we are going to want to do instructions with output. This is going to be the result of a map accumulator R from data.list, so I'm going to need this L prefix. Our function is going to be a step function for now. The starting accumulators, so the list of registers that need to be in the output, will be the terminator registers from the block terminator. We are going to use the function we've just created. And the list on which we are going to do this accumulation is our list of instructions. Now, we just need to write the step function that, given what is the order of the arguments again, it is the accumulator and the value returns tuple. Okay, so I'm just going to type it for now. This is going to be taking the accumulator, which is a hash set of register. It's going to take the value, which is an instruction, and return a tuple of the new accumulator, hash set of register, and the output in our list, which is tuple of instruction and hash set of register. Okay, so given desired output, what is our function going to be? Well, it's going to be different for each instruction. So let's have a look at what an instruction is. And we will have to handle every single case here. Now, at this point, we're still not doing the code generation. I'm just going to close this for a second. We're still not doing the code generation, so at this point, we only need to care about what registers are required past this point. I need to also be careful. I think for almost all of those, this is the target first. This is argument 1 and argument 2. Oops. And those are constant, which I think I can safely ignore in the context of this function. And those I do not remember because it's been too long. So for now, we're just gonna ignore. We will see when we get to those. And invoke, those are function calls, but it depends on this is there a return value? Okay. This is irrelevant. This is absolutely not. Func register. Those are the arguments. Okay. Let's start for now by commenting all of this and just start with a trivial case, which is this add. So here we have our desired output, which is a set of registers. We know that past this point in the block, those registers are the ones that are required. Since we haven't done any optimization so far, but optimizations will be done at the IR level, I don't think this is a place where we can do things such as, well, maybe if the target is not in the register, we can just drop this instruction altogether. I think that kind of like this value is not needed phase will be done on the IR rather than at this phase. So I think here we can just assume, yeah, no, this instruction is here because it has survived the optimization phase, therefore it's required. Therefore, target is very likely to be in the desired output. Anything else would make no sense. Now, what is interesting is now we know that target is created at this point. That means that it is not in the output of previous instructions because it is created at this point. So whatever the shape of the stack is before that, well, like it did not had to reserve a thing for the target because that is something that will be added to the stack at this point. However, those two things need to exist before that, regardless of whether they are in the desired output or no, which means that our result here, desired input in a sense, is the desired output in which we have removed a bunch of things. Let's have a look at the interface of hash set to see what kind of bulk operations we have on it. Because maybe we can do a diff list or something. Oh no, is hackage down again? It's not, thankfully. Okay. I really need to do a thing, but I'll do that offline because it's going to take a while to build a local copy of the documentation of all the packages, which I can do. I have my dependencies cached because Hackage has been. I don't know what's been happening with Hackage, but I don't know if it's under attack or something. But it's been slow recently. Okay, I want to remove elements from the hash set. I think a delete is basically the only thing I have. I don't think there is really a big a other way to do that. So I'm just going to do a bunch of delete. So the desired input will be, I take the desired input output and I apply a bunch of function to it. The first one will be delete of the target. It doesn't need to be in the input because this is where it becomes introduced. And insert argument 1, regardless of whether it was already in the set or not. And insert argument 2. That gives us our hash set for the input. And we need to return now what the accumulator will be for the previous thing, which will be desired input, this new hash set. And we need to return what the value we want in our resulting container, which is this tuple of the instruction and the result. So this is our instruction, which means this function becomes case of the instruction of, and here this becomes instruction and the desired input. Now, there's something that jumps to me immediately, which is that a lot of those things will have the exact same shape, which means we can introduce another function here that does all of the wrapping and unwrapping for us. I'm gonna rename this compute output, I suppose, because that's the output of a... Oh, I'm making a mistake, actually. That is here, what is associated with an instruction is its desired output. Okay, so this is now renamed compute output. However, this function itself, I'm going to change because I'm going to rewrite it as something else. This is going to be a thing of, because I always know what the shape of this is, it will always be desired input, instruction, desired output, regardless of what the instruction is. So I'm just going to make desired input the actual function for an instruction. There we go. So this function becomes desired input. Only takes the... it needs the output as well. So it takes both of those things just the same, but only returns the new hash set and doesn't need to do all of that stuff, which means we can rewrite this as, again, just a case on the argument that doesn't need to be named. And this is now just this part. And we can remove that part. Okay. Basically, what modifications do we apply on the set? Okay, so with that logic, I think every single one of those is the same, which is convenient, which means I can just copy and paste. I think this is just ever so slightly wrong. Let me do that again. That's better. So all of those do the same thing, to the point that I'm even tempted to introduce another helper function, because this is just the same thing every single time, which is, okay, the target is not, it doesn't need to exist before this. However, the arguments need to. Yeah, when everything has the exact same shape, I'm always very tempted to just make a function for this. Let's make a function for this. And just output is going to be a function that takes a hash set. Oh, in fact, I'm tempted to change this function to be the other way around, and to be a function that, given an instruction, it gives me a function to apply to transform a set, which means here the instruction becomes the first argument. And now adjust output will be something that, given a output register and a bunch of input register, will be giving me a function from set to set. And adjust output, the worst name function ever, target the arguments, will be given some set S, I don't even need to name it. It will be insert, it will be remove, delete the target, and insert, well, and union of from list of the arguments. Okay? So now with this, we can replace all of this by nothing. And we can replace every instance of, in fact, I'm not even going to name the set, because this is all returning, given an instruction, returning a function from set to set. So for all of those, this is going to be, I'm going to replace desired output by simply adjust output with target and arg1, arg2. There we go. In fact, no. Even better. There we go. Now those functions become, those are basically negate of a integer or a boolean, or, and this is just a cast. Those three become just adjust output with the target that is being removed from the set. And oh, I need to be careful there. No, by definition, given the nature of the IR, the target can never appear in its own arguments. Therefore, the order of operation, that doesn't matter. Okay. Okay. Next, what do we have? We have the assign series of things, which assign a compile time value to something. Those are even simpler. Those are just there is no register that needs to be present on the stack before this, because those values will not be coming from the stack. They're known at compile time. So this is just deleting the target. That's easy. And those, I don't know, because it's been several months since I have last worked on this. I guess invoke I can probably figure out. Oh, yeah, because combine is how to combine different registers into a struct value, basically. Get field is how to get a value out of a struct into a register. Set field is how to set a value within a struct, basically. Let's start with function calls, which are surprisingly going to be a bit easier, I think. There's two ways to invoke a function. We have a function that is in a register when we have function pointers, for instance. So a function that is a local value on the stack. And we have a function which is a hard-coded known at linking time name. So invoke a name, invoke a register. Return value will be, does that function call give us a something to put on the stack? So I think in those cases, we have to remove the, I'm just going to rename it target for consistency, because this is where the register in which the return value of the function is assigned, if it exists, because some functions do not return anything and therefore do not have a register. And then it's just the arguments need to be in the output of things before. The only thing is, those are maybe registers, so I need to handle that. And I guess the easiest way is to make this taken a maybe and move the problem there, I suppose, which means this become just target everywhere, because all of those are not a maybe. And this becomes therefore adjust output of the target of the arguments, which is already a list, I believe, so I don't need to do that. Let me just check that this assumption is correct. Yes, those are already list of registers. The only difference is, in this case, we also need to add the function, which register the function is stored in, to the list of the outputs of things before. Okay, so now we just need to decide how we handle this. And this, because this is now a maybe register, and I think this becomes, if we have something, then the function we apply to it is delete. That gives us a function from hash set to hash set. If we have nothing, we use the id function. Okay. Now, I don't remember exactly how I wanted to implement struct, because there's a big thing that we haven't done yet, which is struct size. Since there are no pointers really in that language, because we're targeting something that is stack only, and I don't want to do addressing within the stack, the size of a struct, if it has to be known at compile time, prevents us from having any kind of dynamically sized data. So my plan for arrays and things like this is basically to have a representation where on the stack, it's a series of cells on the stack, and the first one at the start of that value is the size, the number of cells below it that end up representing that value. That makes a lot of things complicated, because anytime I do a roll of 3 variables, well, if I don't know their size, I have to first do a bunch of rolls to duplicate the cell that contains the size to be able to get the size dynamically of all of them, so I can do rolls and so on. So for now, I think I'm not gonna bother, for the sake of trying to get something out of this. I think I am not going to bother with structs and dynamically sized data. I think if we get to a point where we can do functions on int, that will already be pretty good. So I think for now, I am going to leave this unimplemented. I swear, one day I will learn how to type. It will make a lot of things a lot easier. Okay, so that should be a first pass at this function. That will give us ultimately this thing here, which is a list of, for each instruction, the corresponding output, what registers are required past this point. We should probably test this, which means that I'm tempted to, for now, give this another name. Annotate instructions. And this only requires, so this is just going to be taking the terminator, and a list of instruction. And this will now return a list of tuple IR instruction and hash set of register. Okay. So we can test this function in isolation, and this is now given a terminator and instructions. This is now just this thing. Which means I could even not name instructions at all. There we go. Okay. So let's try this in GHCI and see what that looks like. First, let's make sure it compiles. It won't, not at first. Because indeed, this will require knowing the shape of hashable. No instance for EQ type for this. Yeah, I probably will want to do the same thing. Which is to make the instances for... Do I even want EQ and or... probably. This really relies, and will need to be documented, this relies on the assumption that really the index is enough and the type is just here for convenience. Which means equal equal is implemented as being equal equal on the register index. And ord is implemented with compare being compare on the register index. Okay, are you happy with this? So far. So far. Okay, so here those I'm using instruction, but it could be either a bytecode instruction or an IR instruction. This is our input, this is our output, which is why I've imported them qualified. I am very tempted to, in fact, remove this type annotation, which is not really required. Here. Aha. So here, those will have to also be annotated with their provenance. Likewise here, those are all the IR things. Okay. Now in scope unimplemented. Okay. That's because I have not imported. I think it's in... Is it in ICE? It is, yeah. Which in this case stands for internal compiler error and nothing else. Okay. Next, what do we have? So here, the compiler tells us that it is expecting this function to be from list of instruction to list of tuple instruction hashed register, which is what we want indeed. But it found something which is from a list of instruction, the last argument of our function, to a tuple of hash set register and instruction hash set register. That's because this function gives us the list of gives us the not just the list with our results, but also the last accumulator at the end. We could check we could do some sanity checking to check that anything that's required past this point is present in the arguments to the block. But that feels like it's just a redundant check that's not actually required. So I think what I'm just going to do is we only need the second element of that tuple. Okay, defined but not used. That's a warning. That means we are close to the end. Yeah, okay. This is just that nothing here is really used. So I'm just going to comment that out for now. Defined but not used. I'm going to underscore for now. Because I have everything combining with W error for now. I don't like warnings. Okay, so this compiles. Great. So now let's go back here and let's do a stack GHCI. I want to use the component 2, which is our compiler. It has to recompile a few things. Is it because GHCI compiles in a debug mode or something? Okay. Thankfully, it went fast. I want to stages generation is what we've been working on. Okay, so now I have, and I want representation IR in scope. We are going to want to try this function here, annotate instructions, to check that it works the way that we want. So what if we have a jump terminator, which takes a target, and target is, I need a label if I remember correctly. Target is a label, and a label is just an int. So let's say I'm jumping to label 2 with register 4 that happens to be a int type, and no instructions for now. Okay, so I'm gonna implement this qualified, so I can say it's an IR here. Okay, so if I have no instructions, then there is nothing to output. That makes sense. Now let's try, and let's imagine that my instructions are a add instruction that to a register 3 that happens, I'm going to create a R function which, given an index I, creates a register I of an int type, just to make this a tiny bit more readable. This is therefore R4 here. Our instructions are an add that targets R3 from register R1 and R2, followed by a multiply targeting R4 from R1 and R3. So after our multiply, the only thing that's required is I4, because, yeah, that's the only thing that's required to do the jump at the end. Our multiply is multiplying into register 4 from register 1 and 3. And therefore, at the output after the add instruction, the things that are required on the stack are only I1 and I3. I2 is no longer required. I4 doesn't exist yet. Okay, that seems to be working. So next, what do we work on? Well, now we can actually do the actual work of code generation, which is to go through the instructions and transform each instruction into actual raw Piètre instructions, basically. So let's do that. Let's see. So this would be this function here, generate block code. I have the function name. I have the block with all of its values. So first, we are going to be calling the annotate instructions on the block terminator. And the block instructions. That's going to give me this annotated list. And what I want in the end is a sequence of instructions. Okay. However, this is a thing where each instruction will result in more, each IR instruction will result in more than one bytecode instruction. So this is a concat map that I want to do. Let me have a quick look at the definition of sequence. Oh, it's in this file. It's in this window. It is a monad. Okay, perfect. So I could do something a bit. I could do a do block in it and just use the monadic thing in there. So that would be for each instruction and stack output that we obtain by doing this. But this is not the same type as this. That's a problem. It means I can't do that. Unless I operate on list and then here at the end do a sequence from list. Would it be worth it to immediately operate on sequences here just because for performance reasons some of the functions might be big, the blocks might be big. Maybe we want to immediately be at sequences for performance reasons. Yeah, I think it's not a bad idea to replace lists when... Yeah, okay. So here I'm going to iterate over a sequence, which means I'm going to change this here to return a sequence as well. This is fine because this function is defined on any traversable, if I remember correctly. Defined in data list. Yeah, it operates on a traversable and returns whatever the traversable is. So this is fine. The only thing as a result is we need to transform our input list into a sequence. With from list. Oops, not what I wanted to do. I wanted to do from list. There we go. It's because it is an is list, of course. Okay. So, with that done, yeah, all list operations are done in this function, so we're good. So now we can do this, use the do block on the sequence using the monadic properties underneath, which is going to basically do a concat map for us, which is what we want. So for each instruction and the desired stack output in this annotate instruction thing, which is the function we've just made, we need to return a sequence of instructions, of bytecode instructions for that particular one, which is also going to be a big case of the thing. Okay. However, no. I am also going to need to know the shape of the stack coming in. So this is not just a concat map. This is, again, some kind of... So this is going to be some kind of concat of a accumulator thing. Let's look at traversable. Let's see what functions there are in traversable. Because I'm assuming the accumulator ones are here as well. Yep, here they are. Is that what I want? Not exactly, is it? Well, I guess it works, and I just make it, I just do... Yeah, okay. I do a concat of the second element of a map accumulator left this time around with a generate instructions function, and my basic accumulator, so the shape of my stack will be the shape of my stack in the input, which for a block... Oh, okay, let me finish this, and then there's a thing I might need to fix in another place of the code. So this will be the shape of the stack at first, and we are gonna be iterating over this. And I'm gonna rewrite this as the other way around. We're gonna do this annotation, and on it we are gonna do the accumulation, and on it we're gonna get the second element, and on it we're gonna do a sequence concat. Okay. Now, what we need here is the shape of the stack, which is going to be what we're going to call initial stack. And the initial stack is going to be, if I reopen my IR here, it is the arguments that were given to this particular block. And there's something I need to check. I'm just going to finish this. So this is going to be a set from list of the block arguments. Now, what I need to check is, are the function arguments properly given as arguments to the first block? I'm going to quit this GHCI, rerun the compiler on... God damn it. I'm going to need to... There's no sequence concat. Is the concat in list on any traversable? It is. Any foldable, of course. I'm assuming there is a concat in here. Yep. Okay. Just gonna go back and have a look at the previous output. If I go back to this test, the foo function here has two arguments x, y. I want to check that those are given as registers as argument to the first label. Yeah, okay. Foo has the first label of the function takes as argument two registers, which are the function arguments. Okay, so that's already working the way I expected. I don't need to go change some old code. That's good. That's good. That's good. So that means this should be fine for all of the blocks of the function. I don't have to make a special case for the first one. So I annotate the instructions. Then I do this map accumulator left thing. And then I take the second element and then I do a concatenation. This is kind of a concat map, but more of a concat fold map kind of thing. Okay, so now how do we generate the instructions for a given instruction? How do we generate bytecode instructions for a IR instruction? I just want to have a quick look at the order of the arguments in this map. It is the accumulator, then the element. So that will be our stack followed by the instruction. And this needs to return the new stack and the sequence of instructions. Okay. So it is going to be another case of let's look at all of those things. I wonder if I could use laziness and the time traveling monad of TARDIS, it's called TARDIS, to do a thing where instead of doing one traversal from right to left and then one traversal from left to right, I do only one traversal from left to right, using the backwards capabilities of TARDIS to do the right to left traversal at the same time. It should probably work as long as all of the laziness resolves at the end. I think it's probably better to keep them separate. So keep it to 1 for now, just to see what I'm doing. And here I'm gonna open, that's gonna be a bit too small on the stream, the bytecode. That's more readable. I have even a tiny bit more space. I'm gonna do that. Okay. Okay. So now here is where everything happens. We have, this is the shape of the stack. That will be, so that will be the list of the registers on the stack at this point. We need to, oh, actually, this will be instruction output registers. And this will be therefore a case on the instruction. So to make an add like this, what do we need to know? We need to roll those registers to the top of the stack and then put that target there. So the question is basically, are those things required past this instruction? Are they part of the output registers? If no, I can just bring them to the top. If yes, I need to duplicate them. Okay. So in essence, this is going to be, I'm going to write down some pseudocode to give us an example to work with. Let's imagine that so far our stack, which will be ordered, so probably a list or something, will be Okay, at the top of the stack, we have register I4, and below that, we have registers I2 and I1. This is an add instruction that does add I5, I4, I1. And let's say that our output, the things that are required moving forward, are the set. So that's our stack. That's our instruction. And our output registers is the set I5, I2, I1. But crucially, not I4. So if instruction, I can't type. So the output of this will need to be a roll. Well, pushing the arguments for a roll. So probably will need to be... If we do something naive and not try to do optimization, the first argument is I4. So this will be first bring I4 to the top. So that will be push 3, push 2, because it's a roll on the 3 top elements and a roll of 2. And for now, I'm assuming that every register is only of size 1. Because when we have strings and vectors, this will no longer be true, and this is where things will get complicated, but for now, I'm making that assumption. So this will be push 3, push 2, roll to bring, after which we will have I2, I1, I4, and I4 will be on the top. Since it doesn't need to be... Since it doesn't need to be kept past this function, it doesn't need to be duplicated. After which we will have... We need to bring the second argument, which is I1. So we'll have a push 2, push 1, roll, duplicate. After which we will have I2, I4, I1, I1. Then since we've now made a duplicate, the duplicate needs to be pushed back below the previous argument. So this will need to be a push 3, push 1, roll to make it... I'm just gonna put those as annotation here. So that after this, we have I2, I1, I4, I1. And then we can do an add. Okay, a few things that come to mind immediately. I need to check here. Here, if I do this, I took care of the first argument I4 first, which puts it second on the stack, which would mean that the add instruction here would have its first argument in the IR, the second argument on the stack. I don't think this is compatible with what we have designed so far, which means this would already be wrong. Second, I need to check how Piètre roll works to make sure that those arguments are correct. But minus those issues, this is more or less what this function needs to do. It needs to give us the push 3, push 2, roll, push 2, push 1, roll, duplicate, push 3, push 1, roll, add, basically. Okay. first, let's check how the roll works. Roll pops the two values of the stack, top two values of the stack, and roll the remaining stack entries to a depth equal to the second value popped by a number of rolls equal to the first value popped. Okay. So that means all of those are wrong. Wait. So the depth is the second value popped. Wait, no, this is correct. Because this will be the second value on the stack. So 3 and 2 is the number of rolls. So no, this is correct. Okay. Perfect. Now, let's have a look at subtract. Aha, pops the two top values of the stack, calculates the second top value minus the top value. Huh. How did I translate in the lowering? I have it in scope. Let's look at an expression. How did I translate a subtraction expression? It is a subtract of the left-hand side and the right-hand side, basic binary operation. Compute the expression of the left-hand side. Okay, so A minus B would be represented in our IR as subtract target A, B. So this would need to be, A would need to be the second value on the stack, and B would need to be the top value on the stack, because second top value minus the top value, which means that in fact, this thing, where the first argument of the instruction ends up being the second element of the stack, is correct. Okay. Okay, that is tricky. I'm gonna shrink this a tiny bit just to have more working space here. How do we do this? So this is going to be for each argument, roll that argument at the top, then add the add argument, the add thing. So this is going to be there again, a concat map of a bunch of sequences. Okay. So zip with bring arg and what I'm going to zip in with is going to be 0 because I need to know how many arguments I've dealt with before, and my list of arguments is going to be arg1, arg2. So this is going to function that's going to do one step of this, which is going to be the roll to make the argument pop to the top of the stack. This will require knowing stack and output registers. This will give me a list of sequences of instructions that I will then concat, and I will add one element at the end of the sequence. What is the operator I am looking for again? this one. At the end of the sequence, I will add one additional thing. After having brought all of the arguments to the top, I will be doing one thing, which is adding one add instruction. Okay. Okay. Which means I will now need a function bring arg, and I'm tempted to make that a separate function just because it's going to be monstrous. Okay, the noise cancellation seems to work. Bring arg will be the function that, given a stack, which is a list of register, and in this case, and also therefore a hash set of register, which is what we need moving forward. And those two arguments, which are going to be just an int, which is an number of the index of the argument I'm dealing with, starting at 0, followed by a register, which is the argument I am looking for. The output of this section will be, there again, a sequence of instructions. Bring is not a great verb. Either I am explicit and this is bring argument to top, or roll argument, maybe? Roll argument. Now, one thing I don't like about this is that I have no way to know what depth a given argument is, but to search for it. That's not great. Oh well. So I have my stack. I have my output registers. I'm going to name it the same for consistency. I have my argument index. And I have my argument register. What do I do here? Well, first, I would need to So this is where, for now, I'm going to make the assumption that a given register is at a depth in the stack that I can figure out based on... I don't have to do that. I can do things properly. Even though for now everything will be of size 1, I can probably do that. Okay, so first, compute roll, given a stack and given an arg register, this will figure out this part. So let's start with that. First, we compute the roll. I think I'm going to make that a separate function as well, because this one will get a lot more complicated when we start supporting dynamically sized registers, like lists and stuff. For now, we have a list of register. We have one register, and I want to return out of this two things. What is the depth at which we need to operate, which is basically the depth of that thing plus the size of the register itself. And I need to know how many steps, which is just the depth, I believe. Okay. And I'm probably just for convenience gonna swap the order of those two arguments, which means this becomes the first argument here, because now I can rewrite this as being a very simple fold or list-like operation on the thing. Well, it's a recursion on it, but not a fold. And given a register, I can do a case of it's empty. That's an internal compiler error. Because that means we are trying to bring a register to the top and we just did not find it in the list. That is impossible. Something went wrong. I think the context thing I'm gonna remove at some point. That's something I wanted to fix. For now, this is compute role. I'm just gonna give the name of the function. Could not find target register. And the details will be show register, and that's gonna be about it. Maybe I'll write it as being stack, and it's gonna be a go stack where go of an empty list is that. That way I can here show what the original stack look like in the debug message. And then I have my regular go function, which is the one in which things work out, which is there are still registers to compute. And this will probably need to take, this will need a 0 here. This is gonna be ignored. This is gonna be the depth. So here, what do we do? If R is equal to our target, I'm gonna rename this as target. If R is equal to our target, we found it. So the result of this function will be we need to roll all the way to depth plus register size of R minus 1. And the amount of things we need to bring up, number of steps up, is just depth. Okay. This will require, however, having a notion, which will probably not be in this file ultimately, but for now is going to live here for the purpose of getting something to work. Register size is something that, given a register, will give us an int, which is the number of cells on the stack that is required for a given register. And for now, it is constant 1. It will change when we support strings, arrays, and other things. Otherwise, we did not find the register yet in the stack, we need to go recursively at depth plus register size of R on the rest of the list. Okay, that's our compute role. Do I want to, in fact, make this return not those two integers, but already a sequence of instructions? Maybe I want to do that. And this is going to be a case of go 0 stack of, maybe I don't do it as a go. Let depth steps equals go 0 stack in if steps equals 0. So if there's nothing to bring back up, then our result is an empty sequence. There's no need to do any up. That's not true. It is. The duplicate will be somewhere else. This is just the roll. Okay, so this is correct. Otherwise, if we need to do a roll because the number of steps is non-zero, then second value popped is the depth. That means our sequence of instructions is going to be, and I'm going to use a language extension here. Let's look at my byte code. This will be a push int depth, push int steps roll. I'm going to need one small language extension enabled, overloaded lists, which basically allows for types that implement the trait type class from list to be created with a list literal, sequences implemented. So I just type a list literal, and this gets interpreted as a sequence. This basically saves me from typing sequence from list here. Which means I could just do that as well. Okay. So that's our compute role, which does this first part here, push 3, push 2 roll. However, that's not all we do when we do a roll argument. So first we do the roll instructions. We will want to update the stack as well. So do we want to return we probably want this to also give us the new shape of the stack so that we don't need to do the same thing twice, I think. Because if we just get that, we will not get the depth or anything, which means we would have to go through the list a second time. That doesn't feel very efficient. This is probably something we need to do recursively as we do this. Basically, we need to bring... No, we don't need to do that. No, okay, okay. That's a bit annoying. It's fine. No, we don't need to do that. We can just do A second traversal, it's fine. For now, it's fine, I think. Stack after a roll will be the register will be put at the beginning of the at the top of the stack after doing a is it delete? Or is it remove? Delete. That is extremely suboptimal. Performance is not our concern right now, but this is something to keep in mind. We will probably want to redo that at some point. Okay, so now we know what the stack looks like, which means, in fact, this function will need to return the shape of the stack after this. Which means this zip with concat no longer works because now we need to again do some accumulator thing to keep track of the shape of the stack. Because of course. In fact, this was already wrong from the start. Because likewise, so this is going to be, we are already doing a map with accumulator. We're going to want to do the exact same thing there again. I'm going to rename this step function for now, and a step in our top level accumulator will be still something along those lines. But what we will do for a given instruction, we will I'm going to actually say generate bytecode. I think it's a better name. And giving it the stack. And well, it's not exactly a map accumulator. It's not exactly that, actually. That's annoying. Do I want to basically use a state monad? That is my question here. That is my question here. Do I want to, rather than keep track of a bunch of things with an accumulator and a thing, do I just use a state monad? And it's honestly tempting. Yeah, I think I'm gonna do that. I think I'm gonna do that. Can I do it in a way? Can I do it in a way where every step in the monad actually just chains a bunch of new instructions? Some kind of sequential thing? Can probably try to do something like that. Okay, so if I do that, this function becomes a flip eval state. Oh, run state t, in fact, a run state, where I give it the start state, which is the stack, and my monadic action becomes generate bytecode for that instruction. and with the output registers. Now that means that generate bytecode no longer takes the stack as an argument, nor does it return the stack. The stack is now an implicit state through the state monad. Okay. Let me just have a look at run state. I never remember the order of the arguments of the return. Run state will give me the value and then the state. So the stack will be second, which for my map accumulator left is wrong. So this will need to be a swap at the end there. Okay. So now this takes the output registers as an argument, and I can just do a case on the instruction there again. And now this is monadic, and I have access to the stack. Perfect. So here I can still do I can get, for each argument, I can get the sequence of instructions, which will be a monadic thing. So byte arg bytecode, arg's bytecode will be. I don't need to do a for, I have them here, so I can do instead arg1 bytecode will be roll argument of the stack will no longer be there. Do I want to make the output registers? Okay, yeah, let's do that. Let's introduce a bytecode monad, which is just a state T of a stack, which is a list of register. I'm going to actually do that on top of a reader of a hash set of registers. Where a stack is a list of register. Okay. Run bytecode gen will be something that, given a value in a bytecode monad of type A, gives me the new stack, which for a foldable traceable we want that to be the first argument. So this is going to be the resulting stack and whatever the A value is, and this is going to require the hash set of register that we're going to read. This is going to require the initial stack, then the action, and then that gives us this. Again, state gives us first the value, second the states are going to need to flip. So run bytecode gen, given some output registers and a stack and an action will be action. Yes, sorry, this has become extremely not beginner friendly. Let me finish this and I will explain in a second. When we're gonna then do a flip run state T, and that's gonna. This is less compiler and more Haskell stuff. I was gonna say nonsense. It's not nonsense. Haskell shenanigans, I think, is a better word. Run state with the stack, and run flip run reader with the output registers and swap. Okay, so the main thing I'm doing here is I have noticed that a lot of my functions have the same shape, and that is a shape that is inconvenient to work with. As a result, rather than doing a lot of the function passing myself, I'm going to use a thing that already exists in the language, the state monad, to do some of that for me. Specifically, my functions that that all have the same shape are all of that shape here, which is I have some state, s, whatever s is, and some argument, and each of those functions returns a new value of type s, which is the modified state, and some kind of result. In this case, s happens to be the shape of my stack. Every step in the generation of the code for an add instruction modifies, like, I need to keep track of where things are on the stack. So every of those functions need to know, okay, what's the shape of the stack as an argument? What's the shape of the stack in after this thing? And each function will take some arguments and will return some stuff. So here, for instance, this roll argument thing, as you can see, has roughly this shape. It takes as an argument my list of register, my stack, does a bunch of things, and at the end gives me the new shape of that stack. So it has this shape where all of my functions take the old state, their actual arguments, their new state. Well, there is a thing in the language where I can rewrite this as being this is a state thing operating on S, and this is a function from A, the argument, or the arguments to state SR, something that knows about an input state, output state, and the result R here. Those two things are basically the same, but we have a nice name here, and by property of having a bunch of language things for this, keywords and type classes, traits defined on it, this makes working with a function of that shape a lot easier. The other one I'm using is reader, which is when you have a bunch of functions that have the same shape, which is they all take an additional, I'm going to call it R, let's call it Z. On top of their result, you have bar 1 that takes Z AR, you have bar 2 that takes Z and B and returns some kind of R2. It doesn't depend. All of them have in common the fact that they take a same value of type Z that never changes, and you have to do the chaining. In this case, for those functions, it's the output registers. When I'm doing all of the steps to generate all of the instructions for my function, like add here, and I'm doing this push 3, push 2, roll, push 2, push 1, roll, take, and so on, I need to know my output registers, but they're never going to change throughout this. In the same way that for state, that's a thing that gives me there's a name and a pattern to all of my functions take a state and return a new version of the state. That is, this thing is basically, this takes an A and returns a reader of Z and R. And bar 2 is take a B argument and returns a reader of Z and R2 or whatever, which means, for instance, this function here, roll argument, with this change, as you can see, it takes the state as register a reader of this thing. I can rewrite it to now be, this is implicit, this is implicit, this is a function that takes an int, a register, and returns only this thing, but it returns them in a reader of the hash set of register inside a state of a stack, which is my list of register, which is this slightly unwieldy type. So this is a function that, given those two things, will return this thing I care about with the context of we have a reader of this, a state of this, and I have introduced a type alias, which is, this is my bytecode monad, which I could just call bytecode gen, in fact. So this is now a bytecode gen of a sequence of instruction, and those are the same function types, but now all of that logic of I want the state and everything is done for me by the fact that I'm using those language construct of state and reader. Now, that means I have to rewrite this function because it have a slightly different syntax now, but that's fine. But that means that now when I will want to retransform back something that has the state and reader back into something else, I will need to do a run state to remove the state from the top, which takes the start stack, then a run reader that removes the reader, which I will get then my value, and at the end the swap just to get those two things in the right order. So now with this, I can say that one single step in the process of generating the instructions for a block is gonna be running the bytecode generation with my reader thing that never changes, my output registers, with my state that I'm gonna keep track of, which is my stack. And this will be then an action within that particular thing. And this will be, maybe I don't need the generate bytecode function. Maybe I can rename this generate bytecode, and this is generate bytecode. And I do this run bytecode gen, and what the action that I do will depend on the instruction. And when it is an add, Haskell is beautiful. A lot of this is like not trivial for beginners. There's a lot of syntax going on. There's like a bunch of keywords and things, but Haskell is when you get past the hurdle of the syntax is weird and some of the notions are a bit, it gets so elegant and concise. And now this is just, I run the bytecode generation using these things. And when I have an add and it's a target, and the big thing of why we have all of those complicated things and all of this function passing and everything is everything is immutable. I can, this output registers, if I want to make a change to it, I have to create a new value that bears the modification. Everything is immutable. The code that is being generated will be efficient, but at the language level, completely immutable. Hence, all recursion, all function passing like this. But yes, the big hurdle, I think, for beginners in Haskell is not any of the weird math stuff. It is purely the syntax. But here I'm back to this. I am running bytecode generation for an add instruction. And what do I do here? Well, I will be able to get the bytecode for the argument 1 by doing a roll argument, which now only takes the int and the register, which in this case is 0 and register arg1. This 0 is just how many arguments have been done before. arg2 bytecode will be obtained by doing roll argument 1 arg2. And this is operating within the context of the stack being managed and everything. And at the end of this, I can return. If you want to get started with Haskell, I think for a long time, Learn You a Haskell was the book that people recommended. I think there's been a lot better since. I think there's a book called The Haskell Book, which I think is a very good resource. I am not super up to date on beginner resources at the moment, but that's where I would look. Okay. And now after this, I will be able to create a sequence, which will be, so this is a sequence of instructions. This is a sequence of instructions. I just need to concatenate all of those things together. And this will be obtained by doing arg1 bytecode. Come on. Concatenated with arg2 bytecode. Concatenated with one individual sequence, which is just gonna be the add instruction at the end that does not modify the shape of, it does modify the shape of the stack actually. Ooh, I need to be careful. I need to be careful. This is wrong. Okay, so I'm just gonna say, I think I'm gonna create binary operation and this. Okay, which is a function that doesn't exist yet, but will exist at some point. And so this will be operation bytecode will be obtained by doing binary operation. This is the result. Okay, that will be the result of this function. This all goes away. Perfect. I'll move this here. So we have to rewrite run bytecode is perfectly fine as it is. I'm just going to move it here for now. Let's do roll argument that has changed now. I'm going to do block. So there's a few things missing here. First, so this is going to be the same. Roll instructions is going to be obtained by doing a compute roll here. The stack after the roll, I don't need to... I think I'm going to keep this function non-monadic. It's purely a thing that operates on a list. So that means that is in fact a let, which means I need to obtain, I no longer have, I have just arg index arg register. The stack is retrieved from the state with a get. That's the current stack as if it had been given as an argument there. So now I can do compute roll of the stack, and I can modify the state of the stack by putting that new version in it. Perfect. And now, what instructions I return will depend on whether, because I am back to doing this. I'm going to bring this back up. Pa-pa-pum. I am back to doing this. So I want now to decide, is the argument part of the output stuff? So does it need to be duplicated or not? Because if it doesn't need to be there, then I'm free to just keep it there. I don't have to do a duplicate and another roll. Okay, so how do I know whether the argument needs to be duplicated or not? That is basically, is it part of what is now in our reader, which is the set of registers that are required to live past this instruction. So if I do a get a view, no, not view, between the lens version and the non-lens version, I'm getting confused. It's an ask s that I want, asks. If I ask for what is in my reader and I do a member function call of the arg register, is that arg register a member of the set which is currently in the reader context of this function? That will give me a true or not thing, and I can decide based on this. So if it's true, I should duplicate. I bind this with an arrow because it's in a monadic context, and now I can do if should duplicate. I could do an if m or something, but I like keeping an if then else explicitly. Then do, and we're gonna do more stuff here. Otherwise, what do we do? If we don't need to duplicate, that's pretty easy. The only thing that we need to return is the roll instruction, which is our sequence of instructions that we have already obtained. So that's just that. There's no need to duplicate. It's already good. If we do need to duplicate, then we do need to do more things. We need to compute another roll there because we're going to need to do a duplicate instruction. And then we are going to need to send it below that many pre-existing arguments. Let me explain. So let's imagine that our stack was I4, I2, I1, and we are trying to bring I4 to the top. So we did that, and after the instructions here, and after doing this modification to the stack, we've now completed the roll instructions to have instead I2, I1, I4. But we must duplicate I4. But since it needs to be duplicated and put back below the current arguments, if this I1 was on the top of the stack because it was an argument we had already rolled, it needs to be rolled behind it. So if I1 was one such previous argument, if the index here is 1, there was already an argument at index 0, and therefore this I1 is the previous argument, then after a duplicate, we will have I2, I1, I4, I4, but we will need to roll it below the list of arguments. So we will need to have I2, I4, I1, I4. We will need to roll it back below the I1, basically. So that will depend. That was only going to be the case when arg index is greater than 0. Because so we can get the duplicate instruction, that's trivial, but we need to make sure we modify the shape of the stack. What I want to be very careful here with is I am carrying around the shape of the stack, but it is not the instructions I'm generating that change it. This is just something I keep track of separately. So I need to be very, very careful that it doesn't get out of sync, is the big thing. So here I will need to modify my state to make sure to indicate that I've done a duplication. And that's going to be a modify of the state that given a stack will give me the new stack. And this is going to be take one of the stack at the beginning of the stack. That way I'm not trying to do anything. Okay, so that my state has been changed, and now I need to compute a roll. Or do I, could I avoid this? Can I avoid this? I can probably avoid this. So what is the roll I need to do in this case, in this exemplary, in this imaginary case I was doing? I need to roll by the size of my argument twice, because it has been duplicated, plus the size of that many things if that thing is greater than 0. Okay. So that will be, we have a size, right? Thing, where is it? Register size. So this is map register size of take arg index plus 1 of the stack. Okay, so my stack currently looks like this. I take arg index plus 1 element from it. I map register size, and I do the sum. And that's my depth. And that's register size of my argument plus that sum. Because it's not called arg, it's called arg register. So that tells me how deep I need to do the roll. And the number of steps. Oh, is it -1 there again, just like it was here? I have 2 copies. Let's say arg index is 1. By taking arg index plus 1, I'm taking the current pre-copy register I want to copy plus the next one. So that's their sizes. Plus, that's not completely correct, is it? Oh, I need to be careful. I need to be careful. So, I have I2, I1, I4 currently in my stack. I will duplicate I4. I am trying to compute the depth and the amount of this roll, knowing that this will need to take into account an additional I4 that doesn't exist there. The depth will be the number of cells in I4 plus the number of cells in I4 plus the number of cells in I1. So it is the register size of this plus this. I think that's correct. However, number of steps will be that. So I can isolate it here. This is the sum of mapping the register size to the argindex plus 1 of the stack, and the depth will be that plus the steps. And I only need to do that if if arg index is greater than 1, is greater than 0. So if should duplicate and arg index equals 0, then what do? We return out of this function. We don't need to do anything beyond. So we need to modify the stack with, as we were saying, take one of the stack added at the beginning of the stack, and we return roll instructions plus just a duplicate, and there's no need to do anything else. If we should duplicate still, but we didn't match this, then the arg index is greater than 0. What do? This is where we do all of this. And that means we return the instructions that we're going to return are going to be the roll instructions plus, well, those roll instructions plus a duplicate, a push int of the depth, a push int of the steps, and a, well, not IR, that's incorrect. Bytecode duplicate, bytecode duplicate, bytecode push int, bytecode push int, bytecode roll. And we need to make sure that here we have modified the stack in our state, so the stack will be modified. I'm going to be removing, so I'm going to be removing the first arg+1 things out of the stack to then insert a copy of the register there. But I probably don't want to actually... I probably don't want to modify the stack at all there, because the binary operation will delete. But I need to know what shape. No, I need to do that so that I can... this is tricky. For now, I'm going to do this nonetheless, just to make sure I keep track. So after this, what will the stack look like? It will be take arg index plus 1 of the stack plus arg register added at the beginning of drop arg index plus 1 of the stack. And here I'm gonna do instead, this is gonna be the post roll instructions, which might contain another roll. So I'm not returning, I'm just returning this part. In the case where neither of those did match, what do we need to do? We don't need to modify the stack. We don't need to duplicate anything. That's just, we return a list of no instructions. Okay. So after this, the stack is in the correct shape. Yeah, okay. So here, after all of this, I have modified the stack to reflect the changes of the roll, of the duplicate, and of potentially the roll afterwards if it's required. I can return all of the instructions knowing that underneath the stack has been modified properly as required, and that will be the roll instructions and the post roll instructions. Okay. That should be all for this function, which means now I can go back here. In the case of an add, I roll argument with 0 previous argument, and it's the arg1. I roll argument 1, and it's the arg2. And then I need to do binary up. What is binary up? This is going to be a function that, given a bytecode thing, one of those, will perform an operation inside our bytecode generation context and will also give us a sequence of instructions. Although here I don't really need to do much more than just, this is just keeping track of the stack basically, because binary operation given some bytecode. Oh, I need to check something real quick. I know that all of those destroy the like pops values and then pushes the result, obviously. I'm curious about out pops the value of the stack. Okay, that's good to know. Although here, no, I need more than that. I need to know the target. So this is the register in which we are doing this. So what we're going to do here is modify our state. The stack is going to be modified. It's going to be now the target at the top of the stack after dropping 2 values from it. And the corresponding instructions are just that 1 bytecode thing. I'm bundling it as part of this so that I cannot create the sequence that contains that bytecode without also modifying the stack. Okay, and now that should be everything for this. We have done all of the work of this. Given a stack like this, an instruction add that to a register I5 adds I4 and I1, and knowing which registers need to come after should be doing this sequence of push, roll, roll, push, and so on, and duplicates as required. Which means that under the assumption that this is correct, which is a very big assumption to make, but you know, subtract will be just that. To the point where I am very tempted to make a new helper function, which is gonna be generate binary up bytecode, and maybe this function needs to be renamed differently. This is apply binary up. Maybe, there we go. And generate binary up is gonna be given a target, an arg1 and an arg2, and a bytecode thing will be that. Roll the argument 0, which is arg1 here, roll argument with 1 before that, which is arg2. That being said, I'm only ever using arg index with +1. Do I want to start them at 1? If I'm using them 1-based, then maybe I should do arg1 is 1, arg2 is 2, which means here this becomes, if it's 1, I don't need to do any roll, I can just do that. And otherwise, this becomes just arg index, I don't need to do the +1 anywhere. That's probably a bit cleaner that way. Okay. Okay. And so generate binary operation given a target, an argument 1, an argument 2, and a bytecode, which I might even give as it's fine. We'll do roll argument 1, arg1, roll argument 2, arg2. Apply binary op of the target and the specified bytecode thing and return the list of things. And under the hood, this will have maintained the state as needed. This means that this now becomes generate binary operation for target arg1, arg2 with the add bytecode at the end. And this becomes the subtract here at the end, but is otherwise unchanged. Okay. Now that means I can probably start implementing a bunch of them, all of the binary operations. Multiply, divide, modulo, exponent. Except, is there an exponent? There is no exponent operation in... There is no exponent operation in Piètre. That means I'm going to have to implement it manually as a loop of multiplications. Oh no. I say, oh no, because if this ends up being an actual loop and require actually doing jumps and labels and everything, then this has to be done as part of the IR lowering and not as part of the code generation, because I am at the point where I am assuming that the control flow analysis has already been done. Yeah, I don't think there is an exponent. And I have no guarantee that I know the value of the exponent at compile time. So in some cases, this will have to become a while loop, which means that this exponent thing cannot exist in the IR. At too high level, we're gonna need something else. Okay, that's annoying. That's something to fix for later. I'm gonna add a comment, which is like, remove this. For now, I'm just gonna make it so that the ones that do have, so multiply, divide, modulo, greater. Yeah, I think most of those I can do. And I can probably do those as well. Where was that? It was... Let's roll argument. There we go. That's here. Oops. Is that enough? Nope. Now it is. So those two have been taken care of. Exponent will not be part of the IR anymore. Oops. I will want to do a thing where I replace every new line by space arrow. Well, first target arg1, arg2 with just, well, I can do a do block, but it doesn't matter. Some amount of space that will fix. And then this will be generate binary up with target arg1 arg2 and bc dot something. I was a bit too generous with the spaces there. I didn't think that I would need a while loop to make exponent in the code generation. That's a lack of foresight on my part. So this is multiply. The IR multiply translates into a multiply of in the byte code. Divide is divide. Modulo is mod. It's named differently. Now the comparison ones are interesting. Cast is interesting. Cast will require some code generation. Oh, this might be a problem as well. Because cast might fail, and therefore a cast, the code that is inserted at runtime, is something that might branch, because it is a if the value cannot be cast, panic, otherwise do the cast. So likewise, cast cannot be done, like some work needs to be happening before that. So that's not here. This is fine. This is in the lowering part. When I do cast, where are you, cast? Yep. Do we want to insert cast bound checks here? The answer is yes. Because those will be branching, and therefore they might end up creating a new label, a new block, changing the control flow analysis. Therefore, this cannot just be done at code generation time. Unless it can. Since this is a panic, and panic are unrecoverable, I could do a push address panic and return, basically. And I would be fine without, but that would still be a branch. That would still be a branch because I would need to be able to do that and then continue to the cast in the case where I don't need to. But I could probably do it purely in code generation if I know that there's an address I can jump to for reporting cast errors, basically. Yeah, maybe I don't need to do that here. I'm gonna not do this evening. I'll think about it off stream. I'm just not gonna do a cast this evening, I think. Okay, so now the comparison ones are interesting because there is more than one operation being performed here. Because the only thing that exists underneath is greater. So I'm gonna make a change. This takes a list of bytecode, or rather, it takes a sequence as well. Just returns it unmodified. Again, this function is here only because I care about the side effects. And as a result, this is also going to take... that's the same. Okay, that doesn't change. And now this is a list, only an add, only a subtract, only a multiply, only a divide, only a mod. How do I do greater or equal? How do I do greater or equal? How do I do greater or equal at code generation time when I only have greater? How do I do equal for that matter? Will I need to revise a lot of my lowering into IR to introduce more things there? Because, for instance, I already did some of that work for if I look at a Boolean and expression, for instance, here I do all of the thing where I branch based on the value of the left-hand side to short circuit and avoid computing the right-hand side if not required. And I insert a second block and so on. Like all of those branches and jumps and other things are based on the fact that I do short circuiting. So here, this Boolean AND expression is translated into a series of jumps and blocks and everything that do not require knowing about an AND at the bytecode at the IR level, because I know that the language will require things that cannot be expressed purely at the IR level. So there's no Boolean AND, Boolean OR at this level at all. I am starting to think that compare for equality, for instance, will require something similar to this, where I will need to do a not greater and not lower, basically, because there is no equality operation in there is no equality operation inside. Furthermore, even greater, I think I'm going to have to redo a lot of this just because I'm targeting such a limited thing where I'm going to have to do a bunch of jumps, and I have to be aware of this at the IR level because I can't just use the greater thing. It can only be used to compare to individual cells. If I'm comparing registers that contain more than one thing, how do I do compare expression at the moment? Yeah, for now I'm just using, well, my IR supports having this, so I don't bother. I think every single operation like this, that for now I have a thing in my IR that in fact cannot be implemented purely with instructions at the Piètre level and requires branching. Anything that requires branching will need to be translated into things in the IR that don't, so those are wrong, basically. Okay, so there's gonna be more work that we need to move back to the IR. Okay. So, I think none of the comparison functions I can do. Negate, I might be able to do. And negate Boolean even more so. Because I think not 0 if it's non-zero, 1 if it is 0. So not Boolean that is trivial. Okay. I'm just gonna do this quickly. Beg your pardon for a second. Okay, not important. I might actually just do apply unary op is apply op n1 and apply binary op n n which just takes the n argument here, and that's the n here. There we go. So apply unary op is just apply op n1 and apply binary op is just apply op n2. Okay. Which means I could even rewrite this as being generate op given a, I can remove this entirely. Given a target, a list of arguments, and a thing of bytecode, arg's bytecode will be a traverse it will be a 4 of zip1 args. That's gonna give me the arg index and the argument. And for all of those, I will do roll argument arg index arg, which I can rewrite as a traverse uncurry roll argument of zip1 args. There we go. That gives me a list of the different arguments. And this will be apply op n, and the n will be the length of the arguments. And this will be concat of the args bytecode, and I don't even need to do that, which means all of those binary up become just up. Oops. I've had this typo the whole time. Oh well. Okay. Which means now I just need to rewrite generate operation target arg1 arg2 as giving a list arg1 arg2. There we go. And for negate, there is only one argument. So the list only contains one argument. For a negating a Boolean, that is just what the not operation is for. For a negating a integer, this will be a tiny bit more complicated because it will be a push int 0, a roll on the size of the, well, I can assume that it's an int, therefore it's of size 1. So this is a push int 2, which is the depth 2 for a roll, a push int 1 for the steps, a roll, and a subtract. Okay. What other operations can I already do at this point? The assign are probably straightforward. I might want to support them if I want to test some stuff. I can at least do assign integer. It's getting late, I am getting tired. I'm typing even worse. Target, and this would be a int literal. Here I might not need this, because this is purely return a push int of the int literal, which means the stack is just modified by adding target at the beginning. And that's about it. Okay. And everything else for now is unimplemented. Let's try to compile the last few hours of work. That's correct. I changed its name to bytecode gen. Swap. Swap comes from pair, which is data tuple. It's not in my prelude. I'm surprised. I might... yeah, we'll see. Okay. Oh, I suppose. Yes, when I go through a block, instruction by instruction, the stack I am using in my state monad thing is not a set, it is a list because the ordering matters. So block arguments it is. I don't need the initial stack here. Oh, so this gives me a list. Why would it believe? So it is saying that this concat here is expected to be a sequence from list of instruction to a sequence of instruction. And in fact, it is a sequence of list to a list. That's because, for some reason, the content of the sequence is a list of instead of itself being a sequence. So something here in generate bytecode believes that the output of this because of this concat, I believe. So to check this, if I annotate this function with this is a register, this is a list of register, this is a list of byte code, just byte code, and the result should be a, well, in fact, no, this is a sequence of bytecode. Maybe that's the problem. Well, that's a BC instruction unresolved. The result should be a sequence of instruction unresolved. Where are you gonna be unhappy? Unhappy with me? Probably on the concat. On the concat indeed. Somehow. Oh, is it because of the... Yes, I think I know what's happening. So this is taking a stack, an IR instruction, a hash set of register, and this is returning this sequence right there. I think this is because of my use of the overloaded lists. Yes, this is generate bytecode. That makes the compiler slightly confused here because I do a pure of a list. Okay. Oh, is it just that I've given the wrong argument? Because now this takes... Oh yeah, the I don't need to give the block arguments here at all because they are available as here and they don't change. So that's purely the instruction. The output registers... Wait, no, I'm an idiot. What am I doing? I'm doing nonsense. Sorry. I think I'm tired, which means it's a sign that I should probably stop. This is wrong. This is already returning stuff in the bytecode generation monad. So that type is wrong. That's going to make things worse if I leave it as it is. So let me just think about this again. I think this was here. I was giving things that do not make sense. Yes, how did this ever work? I think here, this was correct. I do need the hash set of register. That is the thing we have created the annotate instructions for. But generate bytecode doesn't need... Oh, no, it does need the initial stack, which is the block arguments. So that was correct. So this type was correct. This type was not. Because this does the run bytecode gen. Oh, but since it does the run bytecode gen, no, this returns a stack here and this. That is, I think, the correct type now. And now this concat... So expected, given a sequence of sequence, written a sequence, which is what I thought I had. But it's saying it's not able to figure out what this thing is. Interesting. That is probably because of my use of overloaded list. Because if I look at this concat, I'm using the one from this module, but it still is defined on the foldable. Oh, it is defined on foldable, but this concat expects a list as within the argument. That's not what I want. Is the concat of foldable more generic than that? It should be, right? It is not. But as a result, then I want a sum that. Well, no, I don't want a sum. Well, it's just like m sum but generalized to alternative. I think I don't have no, I don't want monad plus. I want monoid is what I want. Well, except no. Because mconcat takes a list. That's ridiculous. Hugel to the rescue. I have some kind of monoid, a thing that can be concatenated, and I have some kind of foldable F. Maybe not foldable, maybe traversable makes more sense. No, I think it is a fold. That's what I want. I want a fold. There we go. Fold. There's probably a few places where I have a concat where I actually want a fold in the same way. So that's the most generic possible thing. I have something that can be folded that contains things that can be concatenated. That is the most generic version, and that's what I want. Okay. So now I think we're encountering no longer weird bugs of fold and stuff and concat. We're actually getting real issues. Rising from a functional dependency between. So here, something is wrong with this. I am assuming that something in this expression does not match the type that modify expects. So modify is something that comes from state. Here's modify. Given some kind of state stuff in which we are, and we operate on some state S, I give it a function from old state to new state. So here I'm giving it a function to a stack associate. Take argindex of the stack and add that, basically. But I don't think this last... Oh, it gives me another error. Is it just a matter of argument priority? Would this work? Yes, and now I'm down to warnings. Define but not use function name. I can just comment that out. This binding for generate bytecode shadows another binding for generate bytecode. Where's the other generate bytecode? Oh, that's a top level thing here. So generate instruction bytecode. Generate instruction bytecode. Let's avoid a shadow. Stack shadows the existing binding at line 104, which is this one. I guess that's true. I'm just gonna name it S here since it doesn't leave past this line. I think it's fine. Likewise here, since it doesn't live past this line, I think it's fine to just call it S. Okay. That's annoying. Okay. I guess I could make roll instructions here. This compute roll thing. Be aware of the... maybe not. Maybe not. This is just a warning. I could choose to ignore it. The warning being that this stack here shadows this stack here, which I am okay with. That being said, I could do instead. Steps are obtained by doing a get s that, given some stack s, computes. So this is just get s of the sum of map of register size of take arg index. It is not just a stylized lambda. There is an operator that is everywhere in the code I've been writing, even though it doesn't show up, which is this. And it is specifically this operator named bind that is the Haskell logo. What happens when I do a do block like this and I write stuff that looks like imperative code, this is actually translated at compile time into a series of expressions. So something that looks like this, A equals x4 and B equals y5 and C is Z of A and B. This gets translated at compile time into x4 bind into a lambda that take A, and that does y5 bind into a lambda that take B, and into something at the end here, let's say, I don't know, pure A, B, C to have a value at the end, and then this does a Z, A, B bind into something that takes C and returns just that pure A, B, C. Do blocks are translated at compile time into something that uses this bind thing absolutely everywhere. It is so omnipresent that it is the Haskell logo. I think something close in OCaml is this operator, but I don't know OCaml well enough to guarantee that it's the same. Okay, so now with this, I've made, I can also remove a $sign here. HLint would tell me about this. Okay, this compiles. That's good. So now what I would like to test is I probably want to generate all of block code and try to see something. So let's go back here. In fact, let me do it in a separate terminal just so I can keep this one free for if I want to run things. And let's load our code again in GHCI. Okay, now let's do import generation, import IR, and in fact import it qualified because I will want to be able. There we go. So let's create a block. If I go back here, what is a block? I'm gonna remove stuff now that we should be done for most of this evening. So let's do a block. Let block equals, that's a block that contains no parent. It's the root block. I'm gonna create back this function R that makes a register. So our block is going to be a block with no block parent. Its argument will be register 1 and register 2. Its instructions will be, let's see, an add into R3 of R1 and R2, a multiply into, I need to fix this. The second instruction will be a multiply into R4 of R3 and R1. We will have then a IR. Is it negate? Negate. Negate I into R5 of that R4. And that's going to be our instructions. And then the terminator will be the end of the block. And it's going to be, let's say, a return of just R5. There we go. So that's our block. No parents, 2 arguments I1, I2, instructions add I3, I1, I2, multiply I4, I3, I1, negate I5, I4, block terminator. Okay. Let's try the combination of all of this evening's work. Generation. Let's try generate block code of, it doesn't matter what the name is, and this block. Generate block code of undefined and our block. Okay, we get duplicate push int, roll, add push int, roll, multiply, push. Okay, okay, okay. We didn't get the return, so there's something that's wrong already, which is that to generate the block code, we will have this thing and the instructions and everything that's going to give us the instructions. This will be instructions bytecode equals all of that. But we will also need the terminator bytecode, which will be just a matter of like calling another function that doesn't exist yet. Just gonna be probably generate terminator bytecode. Oh, this will require knowing. Oh, this is tricky. Okay, so this will be. This will contain the stack at the end, final stack. So I don't need the second and the fold here. Second was because I was getting this, and fold was I was applying the fold on it. I guess I couldn't do a fold here, but I need to keep track of the final stack, which means I can probably now rewrite this as a classic function application No need to involve the other order of operation. Okay. And then the bytecode will be generate the terminator bytecode based on the final stack and the block terminator. And the result of this function will be the instructions bytecode followed by the terminator bytecode, which means now I need another function, which will be generate. And I'm tempted to actually make this function a separate function because it's going to be useful, I think, to have this level of separation where, and then I can do generate terminator bytecode. Okay, which will have a very similar shape, except it doesn't care about returning the resulting stack because at that point it will go away, which means generate terminator bytecode will be something that, given a stack, will do a case of and do some rolls and stuff based on the stuff to do. But for now, for the sake of just testing what I've done so far, I think I am just saying that it's going to be const of an empty list. There is no instructions for the bytecode for now. This is wrong. Maybe I should add to do. Couldn't match. Couldn't match. Yes, this is just taking a terminator. There's no hash set of register here. Terminator here. Define but not use stack. That's correct. Okay, so that's fixed. So now let's go back and let's see if this is correct. So first, we're doing an add of I1 and I2. So first, I'm starting with a duplicate. Yeah, I have warnings as errors for now. I prefer to avoid having warnings at all in the code, which makes, live development like this a tiny bit more cumbersome than it needs to be, but I prefer to be strict on this kind of thing. Okay, so here there's something weird to start with. The very first thing we do is duplicate, and I think that's wrong. So here we encountered an add, so we did this on generate up for the target for the argument 1, which means we started roll argument 1, which is this one here. So we compute the roll. So we compute the roll for I1 at first. Oh, and our stack has I1 on top. That's correct, in fact. But I1 needs to survive, so we don't have any roll to do. I1 is already on top of the stack, but we need to duplicate it. So we duplicate I1. Then we push 2 to roll. I guess. Well, push 2 is weird. Because push 2 does nothing. Why does that happen? Oh, it should duplicate, but it's the first argument, so it's just this case. This push int 2 is part of it is part of moving the second argument to the top. Because after this duplicate, I have I1, I1, I2, and I want to have I1, I2, I1. No, I want to have I2, I1, I1. This push int is wrong. It should be 3. So when we do the compute roll here, when we find the register we want, it is r is equal, depth is equal to 2. So I think this minor one is wrong. I think it's depth plus register size. Yeah. Okay. So I need R, I need block, and I need... Okay. So now I do push int 3, push into roll. So if we follow, we have I1, I2, which is our the shape of our stack at the beginning there. We duplicate, so we have I1, I1, I2. We do a roll depth 3, push 2, roll. So now we have I2, I1, I1. We add. So we now have I3, I1. We push to 1, roll. So now we have I1, I3. We multiply, which gives us I4. We push 0, we push 2, we push 1. So now we have I4 on top, 0 below after the roll. We subtract. We have our I5, which is the result of the negate after the multiply. That seems to be working. Okay. Great. So that means that at a glance, everything we've done this evening seems to be working. At least there is no obvious bug. That means we are now able to generate basic... Well, okay, we didn't do the generating the Terminator bytecode here, so we're not yet at the point where we can generate basic functions because we're still lacking the ability to jump from one block to another. Okay, so I think I'm going to stop for this evening because it's been 3 hours and a half already. Next time, first we do the Terminator bytecode because then we can actually generate functions and we can start hooking up the whole compiler, and that will be nice. And then a big work is going to be finishing all of the missing instructions here, which in turn will mean going back to the IR to fix all of the ones that cannot be implemented in terms of purely code generation and will require some branching. Some of the branching I can do purely at code generation because I can just generate a branch instruction there. I probably don't need to do. I can probably just do a pass through there if required. So I think stuff like cast I can probably do purely at code generation. I don't need to remove this from the IR. But stuff like equal, equal has to be translated to a Boolean AND of not greater and not lower, which is not greater? Huh. I'm not even sure how I'm going to do equality. I'm going to have to figure that out. But those, I think, cannot remain in the IR because they will require branching. And therefore, if I want to have all of my control flow analysis and block generation run and everything, this needs to be translated into blocks as part of the IR lowering and therefore translated into much more basic instructions. So that will be some of the work that we do next time. But that will be next time. Which will probably be on Thursday. I'm gonna try to go back to the Tuesday, Thursday kind of rhythm. If I have some spoons, I'll try to do another one on Wednesdays, but that's not a guaranteed. Okay, I'm gonna stop here for the evening. I'm just gonna quickly. Yeah, there's not a lot of new stuff. Let's just change this to the AR and all of the generation stuff. Uh, it compiles, but this is extremely first. Yeah, I'm just gonna. Which ones will we do? Okay, that's good enough for today. Okay, well, thank you for tuning in. I'll try to be faster than I was last year at putting the recording on YouTube. I'll try to have that done by tomorrow. Thank you for tuning in, and I'll see you next time.